Now we are continuing our program. So we have Guido Sutter from Nestlé, and I want to introduce him shortly. So Guido has a master degree in mechanical engineering from ETH Zurich in Switzerland with specialization in thermodynamics and energy systems and fluid dynamics. He has a long career at Nestlé and in several engineering functions, has built and started new factories in several countries, and he holds the senior engineering management positions in operation and R&D. And now he's a manufacturing sustainability manager at the Zone Europe, especially, and he shows and supports new ways to decarbonize the manufacturing plants from Nestlé across Europe and globally. And he says the use of heat pumps, including temperatures well beyond 100 degrees, is one of the key technologies to decarbonize our food manufacturing plants. So this fits perfectly. I think Guido can give us an overview what is really needed in the food industry. The floor is yours, Guido.
Thank you very much, Claudine. Introduction was already done. So I'm working a long time for Nestlé, and recently I took over this position about decarbonization of manufacturing plants. I'm taking care about the plants in Europe, but I also give support to other zones, and I will come to that, what we introduced in our company. Before we talk about heat pumps, I would like to talk about the number of facts in the food industry and which you may not be aware yet in other places. When we talk about manufacturing in the food industry, we only talk about 5% of the carbon emissions which are generated in our factories. All the rest is generated outside of the factories. A majority in the food ingredients, the raw materials, agriculture, and also the consumers, end use, going shopping, going to the Migros, to the Coop, to the Tesco, to the Walmart, etc., is responsible for about a quarter of the carbon emissions. But even so, manufacturing is only 5%. It doesn't stop our need to decrease and decarbonize our manufacturing plants, because we talk about credibility, we talk about expectations of NGOs, the public, to reduce, and the readiness, to bring our targets by 2050, by 2030. Net zero is the ambition to really go down to zero and decarbonize completely. So when we talk about food, we also have to be aware that some of our unit operations are terribly bad in efficiency and need very, very important rethink in manufacturing. If you think about a pet food dryer, if you go to the average efficiency, we reach around 50%. The pizza oven has 25%. A wafer oven, for Kit Kat, etc., has around 20%. Spray dryers, we are in the 50%, noodle dryers in the 40%. Roasters, coffee roasters are 20%, and we have to imagine that, 20% means 20% of the energy goes to the beans, to the product, and 80% goes straight to the chimney, to the environment. If we talk about the retort, to sterilize pet food, to sterilize soups or ravioli or whatever in a pressure vessel, pressure cooker, most of the energy is just going in and then going out again, heating up steel and water, but not the product. And a PET, preform heater for PET bottles for water industry, we also found out that we only have an efficiency of 20%. So first, the priority is always to increase the efficiency. And many of these developments of these unit operations are now in the hands of our R&D people to develop with suppliers systems, which have a significantly higher efficiency. When we look at the food industry as a whole, we also can recognize that food paper industry is a low temperature industry. Most of our processing is the same as in the kitchen. You know, we are using temperatures between 100 and 200 degrees. And in the factories, this is exactly the same thing. So most of the energy is used at less than 200 degrees compared to the other side of the industry. You know, I'm took here steel and cement, you know, which is consuming 1,500 degrees. Um, I would call food paper industry an easy industry to decarbonize because we have the technologies basically ready already. So when I look then our Nestlé company, so 70% of the energy is consumed at less than 150 degrees. And then we have some high temperature consumers. I come to that later on. So when we talk about sustainable solutions, that means low temperature, medium range, you know, the lower medium range temperature. For sure, we have to electrify with heat pumps. It's a key technology for us to decarbonize our factories. So to identify, you know, the potentials in our factory, we have realized that in the factories there is often not enough knowledge about heat pumps, about discovering, you know, the potentials. So we have organized a methodology to assess in the factories through a process in 1 week. And in 1 week, usually we get the results as the carbon reduction roadmap. We get the capital phasing plan, you know, what we have to invest. And we also get lots of learning across the people. So I give you also the results of it and where we are today. We have assessed already more than 100 factories in all continents. We have covered the carbon emissions already by 65% with these 100 factories. But what's even more interesting, and let me get the pointer, we get on average minus 80% tons of carbon emission reductions. And we also get, and this is financially even more interesting, we get minus 50% megawatt hours per year on average reduction. And here we have a real financial benefit when we go for decarbonization of the food factory. And as a side benefit, we also get some water reductions. That's where we are today. I'll give you a flavor, you know, how such a workshop looks like. In 1 week, we go to the plants, we look at the factory, we have many group works and work out together the plan, you know, for the future up to 2050 in our factories. In this example, carbon reduction minus 82% and energy reduction minus 56. So another thought, in our factories, we have raw material getting into the factory, finished goods getting out of the factory. And the food factory does not change the molecules significantly. Sometimes, you know, we do some roasting, some modification, but generally speaking, raw material goes in, gets a physical treatment, and it's getting out of the factory, typically at the temperature of 20 degrees. So why then are we consuming so much energy where, you know, product goes in at 20 degrees and product comes out at 20 degrees? And the reason is today, how we designed factories in the past for the last 100 years or at least 30 years, there is no heat recovery. There is no heat recycling. You know, we have lots of fuels, electricity, fresh water going into the plant, and what's coming out of the plant is, you know, the three main losses through the chimneys, through the cooling towers, and through the wastewater losses, which exit our plants at high temperatures. If you want to know how efficient the factory works, just go in the backyard of the factory and look how big cooling towers are, and then you know how inefficient our factories work. So the way to do in future is this way. We have to recycle a part of our energy at least to reduce input primary energy and also exit losses. That's the principle what we discuss with our people on the shop floor and try to improve. When we talk about the strategy to decarbonize, we also have to realize that reducing is always the first aim in food manufacturing. You have to reduce, clean less, use less hot water, avoid idling of our lines, not producing but still kept hot. This is the most important thing. And then in this sequence, we should then secondly rethink our way of how to set up our processing lines and eventually also our industrial services lines. And only at the end, we have to think about replacing what cannot be generated with other means, rethink our processing lines or include heat pumps for energy generation. We eventually will have to replace with renewable fuels that can be biomass, biogas, or eventually direct electricity. COP, most important, and I mean, I understand that you all understand the importance of the COP, the evolution of the COP. The higher we go with our temperature lift, the lower is our COP. So I do not want to go more into the detail. What's not understood in our factories, people hear heat pumps and then they think they can solve everything with heat pumps. But in industry, we have to also integrate the system accordingly and make it fit to the use of heat pumps. So we have to change our systems such that our heat pumps work most efficiently. And you have to imagine that for 100 years we set up our factories with a steam generator in one corner, which produces steam of 12, 18 bar, whatever, 200 degrees. And on the periphery side, we are generating hot water to heat up rooms, air at 20, 50, 80 degrees for hand washing or etc. And we have to realize that we have to integrate the system such that it's suitable for heat pumps and also suitable for finance, because we have to cope with that condition. The COP of the system, which is the gain over the effort, with some temperatures, high temperatures, and the temperature difference, and some efficiency factors for the compression, for the compressor. We have to fulfill the condition that this COP of the system is higher than electricity price over the gas price. So this electricity gas price ratio always needs to be higher or lower than the COP of the system. COP has to be higher than this ratio. So what helps us in Europe, if you look at the evolution of electricity generation, in 2024, solar for the first time has overtaken coal electricity generation, and also wind has overtaken already before coal generation of electricity. Now, if you look at the right table, PV cost and wind power cost are the cheapest electricity which goes to the grid and helps us to evolve the electricity gas price ratio from 2.5 to 3 today, decreasing year after year to make heat pumps and electrification of our factories more attractive. Because we have to be attractive, it's not that to be attractive to engineers, we have to be attractive to our management who have to make the decisions for investments. Good. Now, let's talk about heat pumps. You remember that slide? So when you look at the different processes in the first section, less than 90 degrees, you find areas like space heating, chocolate beverage production, ice cream, sanitary hot water, pasteurization. In the second range between 90 and 200 degrees, you find aseptic lines, UHT lines, sterilization processes. Roller dryer is already in this area here. Frying would also be in this area here. And then the high temperature in food manufacturing. We talk about coffee manufacturing, Nescafe, spray drying, roasting, baking. So let's have a few examples of implementation in the first section. So we have introduced heat pumps in the last 3 years with a combined heat capacity of 13 megawatt. Most of these heat pumps, they go up to 85 degrees, some they go to 65 degrees, generating 20,000 tons of CO2 savings. And we also intend to continue with this evolution with another 20 plus megawatt heat capacity to be installed in the next 5 years. So when we go to concrete examples, so this is a project which was started up in 2023, Konolfingen, Switzerland, 1.3 megawatt heat capacity, 10,000 megawatt hour of savings. So you see, this plant is operating nearly 8,760 hours full capacity to use the full heat, from the heat pump, which is here. Heat pumps are not very sexy, it's just an engine, a compressor, and a motor. But what we have usually introduced always in combination with a heat pump is a stratification tank to make sure that differences in heat consumption and heat generation are stored in a half an hour or 1 hour stratification tank in form of hot water. Another example is here, which has been introduced in 2024 in Bissenhofen, a dairy factory in Germany. We are actually doing two projects there, 8,000 and 10,000 megawatt hours per year. A significant saving of minus 21% of the factory consumption of today. Two stratification tank, one for the higher temperature grid and the other one for the lower temperature grid at 85 and the lower at 65 degrees. Another example is in Czech Republic. We are drying jellies there, soft bonbons, sweets, which need to be 1 day in a storage to be dried, finally dried. We have 3 times 1.2 megawatt heat capacity. The savings is a bit less, but still significant for the factory. We have nearly 50% savings. Okay, examples in the second range, and here I cannot show yet real running examples, but I can show a project which is just in front of completion, and we will go exactly the same way as my predecessor speaker has spoken already. We plan to go with steam compressors, MBR. You see the MBR up here, multi-stage MBR to reach the temperature which we require. The plan is to use it in a retorting line. These are retorts which require typically 125 to 130 degrees Celsius, and we plan to pick a heat source at say 70 degree, bring it up to above 100 degrees, and then continue the cascade with mechanical vapor recompression. Not yet installed, but very close to submit the credit, and I hope to have this plant up and running on an industrial scale, 1.1 megawatt heat capacity by today around in 1 year. So when we talk about steam compression today, we have a system, we know it works. We have plenty of pillar fans, high speed rotating fans, about 10,000 tours per minute, rounds per minute in place. We use this mechanical vapor compression in evaporators already today successfully. It works, it's very reliable, very sustainable operation. We know it works. The disadvantage of fans is the temperature lift is limited to around 10 degrees. So if you want to have a temperature increase of around 40 degrees from 100 to 140 degrees, we would need already 4 machines in series, each of the steps, adapted for the flow rate, for the pressure rating, etc. So we are also studying turbo compressors. There are two which are currently in discussion. One is SPX flow, the other one is Johnson control system. The advantage of turbo compressors is they can make a temperature lift of 20 degrees. So instead of having 4 steps like here, we would need only 2 steps of pressure increase or temperature increase with the turbo compressors. So not yet decided which way we will go, but we will certainly go with steam compressors, either the left side or the right side, not yet fully decided. What we also plan to do is to stretch the temperature of ammonia screw compressors from 90 degrees to about 110 degrees. We are working to a company, Filter Copeland, with another type of screw compressors, which allows us to go with ammonia, stretch ammonia to around 110 degrees. We are reaching, system pressures of 80 bar instead of 50 bar at 90 degrees. And then from there, we would combine it either with, say, in this example here, 4-stage pillar fans at 140 degrees, or eventually replace the pillar fans with turbo compressors. So the factory of the future looks something like this. We will have heat pumps as a key technology. We will certainly use new technologies, disruptive technologies still to be developed. MBR, it's a key technology we will use. Of course, some other renewable energy. And some of our factories, we may eliminate steam and go fully with electrification, with heat pumps, and then see what is the backup, maybe steam as a backup, maybe just water heater as a backup, as required in our factories. This is the second last slide. This is a message to our machinery suppliers. When we talk about compressors, heat pumps, etc., our operations design criteria is first compliance. We need compliant machines. We need compliant refrigerants. What we have decided that in Nestlé we are only using natural working fluids. We will not accept anymore any HFC, HF, HFO or whatever, which are, having a risk, an environmental risk, and have the risk to be banned after 10 years, and then we restart to change all our machines. So let's say the compliance issue has to be for the next 100 years. Then, of course, in operation, most important, reliability, safety, and fit for the future. We have to see that, this system we are installing now, they are suitable again for the next 100 years. And then efficiency, we have to always aim for the highest unit operation efficiency, highest COP, lowest operational cost, lowest life cycle cost, because this will make our management being supporting, heat pumps or not. And I'm coming to the last slide, which is this one here. It's a kind of a 3-stage set of recommendations. Make sure we have the right sequence in our decarbonization strategy. First, reduce. Second, rethink. And then at the last, it's becoming the replace. Then our systems from now to be installed have to be at least fit for heat pump implementation. So if we do not want to invest into heat pump already right from the beginning because we don't trust, make sure that the system as a minimum is heat pump ready, low sink temperatures, high source temperatures, not designed for steam, but designed for hot water, eventually to install the heat pump later on. And again, heat pump is key. System temperatures depend on the sink temperature and the source temperature. So design the systems already with adequate heat exchangers. And with this, I thank you very much for your attention.